For a balanced equation of the form A moles of reactant A react with B moles of reactant B to give C moles of product C and D moles of product D, the reaction quotient QC is a fraction, since a quotient is a fraction. The subscript C, which is placed at the bottom right side of the letter Q, represents concentration. QC is equal to the concentration of product C raised to power C times concentration of product D raised to power D divided by concentration of reactant A raised to power A times concentration of reactant B raised to power B. The power of each reactant or product is its stoichiometric coefficient in the balanced equation. Now for some practice. For the following equations, write reaction quotients QC. Check your answers against the solutions provided here. Make sure you master this skill. For the decomposition reaction of N2O4, different experiments may be carried out and graphs obtained from experimental data. From these, at different times of the reaction, different reaction quotients are calculated. The two graphs here refer to the reaction starting with 0.200 molar of NO2 but no N2O4. Over time, NO2 is consumed and N2O4 is formed. At equilibrium, the concentration of NO2 drops to 0.0204 molar, while the concentration of N2O4 grows from 0.000 molar to 0.0898 molar. At time zero, the reaction quotient is infinite since a quantity divided by 0 molar is infinite. As time progresses, the reaction quotient becomes smaller and smaller until at equilibrium it no longer changes and becomes constant. The point here is that the reaction quotient is not constant and varies at different points in time before the system has reached equilibrium. From the start of the reaction to the point before the system achieves equilibrium, the reaction quotient QC keeps changing. But once the system hits equilibrium, QC ceases to change since reactant and product concentrations stop changing. Recall that QC is expressed in terms of product concentrations and reactant concentrations. If these no longer change, QC doesn't either. At equilibrium, QC now becomes Kc, the equilibrium constant. A constant doesn't change, so Qc is a value that stays the same at a particular temperature. What is the formula for the equilibrium constant Kc? It is similar to the formula for Qc, except that instead of Qc we write Kc. In addition, Kc is only applicable when the system is at equilibrium, not before that. Thus, the concentrations that go into the formula must be those of the reactant and product at equilibrium. This is the law of mass action. That is, for a reversible reaction at equilibrium and a constant temperature, the reaction quotient Qc has a constant value Kc, the equilibrium constant. How do we make sense of Kc? Well, its magnitude reveals the extent or yield of a reaction. If the magnitude of Kc is large, it means that the numerator is bigger than the denominator. Now, the numerator is all about product concentrations, while the denominator is all about reactant concentrations. A larger numerator implies that the product concentrations are high, and a smaller denominator implies that the reactant concentrations are low, which means that at equilibrium there are more products present than reactants. This in turn means that the formation of products is more favorable than the formation of reactants. The converse is true. If the magnitude of Kc is quite small, it implies that the numerator is smaller than the denominator, so more reactants compared to products are present at equilibrium. The formation of reactants is more favorable in this case. Thus, at a glance, the magnitude of Kc gives us a feel of the final composition of the reaction mixture. Here is an example. Carbonyl chloride, COCl2, also called phosgene, is a highly poisonous gas that was used on the battlefield of World War I. It is produced by the reaction of carbon monoxide with chlorine gas as shown in the equation. In an experiment conducted at 74 degrees Celsius, the equilibrium concentration of carbon monoxide was 1.2 times 10 to the power of negative 2 molar. The equilibrium concentration for molecular chlorine was 0.054 molar, and the equilibrium concentration for phosgene was 0.14 molar. A. Write the equilibrium expression, and B. Determine the value of the equilibrium constant for this reaction at 74 degrees Celsius. How do we answer this question? Use the law of mass action to write the equilibrium expression and plug in the equilibrium concentrations of all three species to evaluate Kc. Kc is a fraction where the numerator is the concentration of phosgene and the denominator is the concentration of carbon monoxide times the concentration of molecular chlorine. B. After plugging in the values given, use a calculator to obtain the final answer of 216. You may also express this in scientific notation or standard form. Equilibrium constants have no units. This is because the concentration of each species, whether reactant or product, is compared to its concentration in standard state. So for solute A in aqueous solution in standard state, it is written as A enclosed within square brackets with a superscript of 0. A superscript of 0 in this context is not a power or exponent. Rather, it tells us that something is in its standard state. It has been agreed that the standard state of any solute in aqueous solution is 1 molar. Concentration of A of a reaction has the unit molar. So does the concentration of A in standard state. To simplify units, we take molar divided by molar. Molar cancels. It is similar for other solutes B, C, and D. Therefore, the equilibrium constant Kc is dimensionless, that is, it has no units. You are not required to prove this. Just remember that Kc has no units. Kc reveals how far a reaction proceeds at a particular temperature. There are three possible scenarios. In the first scenario, the reaction goes more or less to completion and the reaction mixture ends up being mostly products. For example, in the reaction between silver 1 ion and ammonia to form Toland's reagent, diamine silver 1 complex, the Kc value is 1.5 times 10 to the power of 7 at 298 Kelvin. This value is huge, so it means that the diamine silver 1 product is favored. Second scenario, for the reaction between molecular nitrogen and molecular oxygen to form nitric oxide, the Kc value is 4.3 times 10 to the power of negative 25. Tiny, thus reactants are favored. Third scenario, the reaction proceeds to some extent, and the equilibrium mixture ends up with comparable amounts of both reactants and products.